Hello, this time I'd like to talk about predicate logic and mathematical statements. Certainly, predicate logic enables us to analyze a variety of statements. We can even determine their validity mechanically, think of through tables, for example. But it provides really little insight onto statements like the square of a real number is non-negative, or the product of two odd integers is odd. Now, the statements that we see here are clearly propositions. They can either be true or false. But at the same time, they're also atomic. We cannot further decompose them into smaller propositions. What we need is a more powerful tool, something that allows us to break these statements into smaller parts, right? At the moment, using our natural language. So let's start with the first one. Say the square of a real number is non-negative. Well, let's see if we can make a translation, right? An equivalent translation to this. We can say something like, for every real number, its square is non-negative. Now, what do we encounter once we do this? Well, I'm going to signal it with a different color because there's something important here. What we have here is some context, right? Every real number. What we have here is a subject with a predicate. The combo that we analyze in elementary school. Yep. From this, we can do the following now. Let me go further. Now, what I want to encode is this portion, the it of the its, right? And I'm going to denote it by a variable, some dummy variable, just that allow me to have a placeholder instead of saying it. Okay. So when I do that, I gain the following. I would say something like, for every real number x, we have that x squared is greater or equal than 0. Now this is a more familiar format, the one that we are accustomed in mathematics. Now later on we'll see whether this is true or false. That's for a different video. For the time being, let's just analyze these statements. I'm going to take a second one. States the product of two odd integers is odd. Let's try to do the same thing, a translation. We have for one integer, tentative translation, for one integer and other integer, well, this is going to be a little bit long. If the one and the other are odd, then the product of the one and the other is odd. Well, quite a while. But one more time, look, what we have here is a context. One more time. And once that is defined, well, we have a couple of subject-predicate combos, right? I'm going to signal here, which are indeed connected by implication, right? So now we see that whatever we have learned from propositional logic comes handy. Okay. So now the power of introducing mathematical symbology is that we don't have to write this all the time, and that's what we're going to do. So that makes the translation much more transparent. And I would say something along these lines. For each integer m and each integer n, if m and n are odd, then m times n is odd. Okay. Now, we're starting to see some patterns, but let's take more examples so that we can justify definitions that we're going to provide later on. So let me move forward. Take another one. Like this one, every integer has a multiplicative inverse. We go for a translation of the statement. Yeah, well, it would be along the following lines. For each one integer, there exist other integer such that the product of that one and that other one is 1. See, well, there's a lot of ones here. Let's see what we can do with mathematical symbology. We're going to just introduce these dummy variables that are going to allow us to get rid of the its, the theirs, the ones, the others. That's essentially what we're doing here. So I would say something along these lines. For each integer m, there is an integer n such that m times n equals 1. Well, I think this is much nicer. Now, one more example that I think it's going to be familiar from grade school. Something along these lines. The system of equations x plus y equals 1 along with 2x plus 2y equals 3 has no solution in the real numbers. That's my statement. Let me make a translation. But now this time, I think the statement is in such a form that we can even guess what are supposed to be the dummy variables to use, the x and the y. So let's just put it right away and kind of skip a few steps, right? The intermediate step where we have everything in full English or full Spanish, whatever language that you're using. Say, there are no real numbers x and y such that x plus y is equal to 1 and 2x plus 2y is equal to 3. One more time, right? One more time, just so that we have it signaled and we detect the patterns. In each of the cases, right, we have a context. Right? Right? Just as we have seen in example 2 and in example 1. And followed by that, we have a series of subject-predicate combos, right? Maybe seasoned with logical connectives. As we have seen here. It's kind of hidden, but this is a subject predicate. This is a subject predicate. This is a subject predicate. Now, what is it we have seen from the examples here? Well, first of all the statements have a richer structure. They have a context and they have a subject-predicate combo, along with logical connectives. Now, the context comes in the form of quantifiers for each, there is, there exists, for every. And along with that, a collection where the subjects are being quantified, like the set of real numbers or the set of integers in the examples that we provided. Now, the predicates depend on some of the variables defining the context. For example, in this one, right, that we have for number 3, the predicate m times n equals 1 depends on the definition of m and n, right? If I just write on its own m times n equals 1 without any context, it has no meaning, right? It becomes meaningful once we declare what m and n are. Okay, so let's do that. Once we know the dependency, we can write it in sort of a template fashion, right, to indicate just the following. So, in this example, right, in number 3, suppose for a moment, right, that instead of writing m times n equals 1, I simply write p of m and n. right? Just to make a translation between these two. And every time that I encounter for every, I will indicate it with the symbol that we use for all. And every time that I encounter there exists or there is, I will replace it with the symbol for that respective quantifier. Now, as you can see, this is just a tilted A, and this is just a flipped E for existence and universal quantification, all, right? And in that context, well, let's do the following replacements. Now, in number 3, the statement that we just had before may be translated into the following. For every integer m and for every integer n, well, sorry, let me just make the correction here really quick. For every integer m, there exists an integer n such that, well, the product of m and n is equal to 1. But since we made the translation, we can simply write it in this fashion. Let's try to do the same for number 4. Well, in this case, we have a negation in front. So we're going to put it. So it's going to be a negation. Well, a negation of the existence of certain things. What are those things? Well, one of the things is a real number. The other thing is also a real number. And what cannot happen is that the sum of those two equals 1, and twice the first plus twice the second equals 3. Well, we can encode that in predicates as well in the following fashion. We can just say that the first one has p1xy. Now I can use a logical connective for conjunction and write it in this fashion. And of course, the translation is that this stands for that one, and this P2 stands for that one. As in the previous case, that P stands for that one. Now let's go back to and complete the details for the other elements. Say for example number 2. Well, here we have for every integer m and for every integer n. Well, here it says if m and n are odd, I'm going to replace it by the following: O of m and O of n to indicate m is odd, n is odd. Then, well, the product is odd, where of course O of whatever indicates that that whatever is odd. And this one, this P, is signified right here. Lastly, we go back to the original example, the first one. And now that's readily translated into the following form. For every x that is a real number, we have p of x. And you may say, well, what is that p of x? Well, that p of x stands for x squared is greater or equal than 0. And with this we conclude. Later on, we can see that now that we have decomposed the statements in this form, we now can proceed to determine whether they're true or false. But that's for a subsequent video. Take care.